So I'd like to explore the question, why did you do that, as a way to think about what's going on in learning. I'm going to start with 4 vignettes. The first one is an 8th grade class, low-performing school, NSF-funded curriculum. And the day on there, the teacher starts with a review of box plot and 5-number summary, and then is looking at histograms. And we've got data on plants. So we've got the plant height, and we've got the number of plants on the graphs that you're going to see. And the students are describing what they can learn from that. So the student says, well, there are small plants, and then there's some tall ones, and then the teacher says, wait. That's a common error. We're going to have to fix it. Let's go back and talk about what information you can get from this. All right, try again. So the student sees the next graph, and the student says, well, they're slow, and then it gets tall. And the teacher says, why are you doing that? We just talked about the mathematical information that you can get from this. All right, let's do a visualization. Maybe that'll help you figure out what the mathematical information adds. So the students do that. They say, well, it's more level and it's more spread. The teacher just gives up, says, all right, I don't know what to do here. So what's going on? So let's ask our question again. Why did they do that? So Veritasium produces science videos, and they produced a video about what we can understand when we watch a video explanation. And in the scenario that they studied here, they toss a ball in the air. What force acts on the ball once it leaves your hand? So in the study, the pretest, 6 out of 26 on the pretest. They watch a good video. Everybody agrees it's a great video. Clear, concise, confirms my thinking. I'm more confident than ever. 6.3 out of 26 on the post-test. And then they watch a video with misconceptions. They reported it was confusing. They're less confident, but they get 11 out of 26. And some of the first group said, well, we didn't really have to pay attention because we knew it already. The second group says, took a lot more effort. So why did they do that? Veritasium says the misconceptions get in the way of understanding. And what do you do about that? Put the student thinking in the video, put their misconceptions there, discuss why it works, and compare it with the scientific. Well, I agree, except I would focus more on connecting to student thinking. And I would say that our job is to help students articulate what they notice and wonder. Don't rush to use the science and math concepts for their thinking, and organize their thinking for comparison and coordination with the other views. So what would that look like? Let's go back to our video. We have 3 dimensions, I'd say. The observations, the experiential, the mathematical quantities, and the graph elements. Spend time thinking in each of those and then coordinate across those. So why did the students hold on to their original thinking? Why did they do that? They did it because we rushed their thinking. They did it because we listened for our ideas rather than listening to theirs. And they did it because they didn't have a scaffold for thinking. They only had a procedure for responding. So what can we offer them? Grade 3, vignette 3, 8th grade math teachers working on a difficult unit in fraction division. And their students are confused, they're exploring all kinds of methods, and they're not getting any better, they say. So I have like 5 minutes at the end of the workshop to address this question. I decide that they're missing what I call the understanding story. And we use concept, method, and procedure. What's the concept of division? We might say, how many of this are in that? What's the method that we use for figuring out how many of this are in that? Well, we can count. And we might have a simple problem, like count the number of unit fractions, and then count the number of groups of those. And then as we do that, what patterns do we notice as we do that? Well, we notice that we're multiplying by the denominator, dividing by the numerator, and that can take us back in there. So now, why we are doing this, that question becomes a question about purpose and design. The concept, method, and procedure is helping us frame both how we learn and what we're learning. So, the trajectory for why do you do that, that question started out as an accusation, you're not paying attention. Then it becomes a correction of a problem. Then it's connecting to student thinking. And finally, it's about generating frameworks to guide and focus the learning process. Vignette 4. Lizzie's a 7-year-old that sits next to me on the plane on the way over. Turns out our iPod battery is dead. I overhear this and volunteer to charge from my computer, and we have all kinds of normal conversations like wireless networking on the airplane that you have with a 7-year-old. At some point she asks, how far is it from my home to her home? And we estimate, and I get 600, 800 miles. And Lizzie says, you know, it took me 2 years to get 834 points in my game until I had enough credits. I said, wow, that's a great way to think about how big that is. We're about to land. She quickly draws this picture, rips it off her book, and hands it to me. This is a good example of why I do this.